Hello, I am Pranayan Raj from Department of CSCAML. Today I am going to explain about the topic 100 lockers. The 100 lockers problem is a classical math puzzle involving 100 lockers and 100 students. Initially, all lockers are closed. The first student opens every locker, the second student closes every second locker. The third student toggles every third locker. If it opens, it will close, and if it closes, it will open, and so on. With each subsequent student toggling lockers that are multiple of their student number. The 100 lockers problem is a classical logic and mathematics puzzle. It demonstrates concepts such as divisor theory, toggling operation, and pattern recognition, applied widely in engineering thinking and algorithm optimization. The problem setup: there are 100 lockers, all initially closed, number to 1 to 100, which is starting closed. 100 students each walk down the row and toggle lockers according to their number. Student 1 toggles every locker, student 2 toggles every second locker, student 3 toggles every locker, and so on. Student 100 toggles only locker 100. The final result of this is after all students have passed, only the lockers with numbers that are perfect squares remain open, such as lockers 1, 4, 9, 16, 25, 36, and so on. This happens because only perfect squares have an odd number of divisors, causing them to be toggled an odd number of times and ending up open. Each locker is toggled by students whose number divides the locker number. For example, locker 12 is toggled by students 1, 2, 3, 4, 6, and 12. Only perfect squares like 1, 4, 9, 16, etc. have an odd number of divisors. So they are toggled an odd number of times and remain open. The additional insights are 10 lockers remain open at the end. This problem is often used to illustrate concepts in number theory, particularly divisors and perfect squares. In general interpretation, the problems involves iterative state transitions in a discrete system. Each toggle each toggle represents a change in system state, open and closed, helpful for understanding switching system and binary operations. Moving on to next slide, the mathematical operations. A locker is toggled once for each divisor of its number. Divisors typically come in pairs. Example 12, 1 into 12 or 2 into 6. Perfect squares have an odd number of total divisors because one divisor repeats. Thus, only perfect square locker remains open. Only lockers with perfect square numbers stay open because perfect squares have an odd number of factors, with all other numbers have an even number of factors. Why we use perfect squares only matters. Each locker is toggled, open or closed, once for every factor of its number. For example, locker 12 is toggled by students 1, 2, student 1, student 2, student 3, student 4, student 6, and student 12 6 times, which is even. So it ends up closed. A locker will end up open only if if it is toggled an odd number of times. Like if locker 12 is toggled by students 1, 2, 3, 4, 6, 5 times, which is odd, so it ends up open. The role of factors. The numbers have factors that come in pairs. For example, 12 has 1, 12, 2, 6, and 3, 4. Each pair toggles the locker twice, resulting in a net change of 0, which is closed. Perfect squares like 16 have one factor that is repeated. 16, 4 into 4, the factor 4 only counts once, so the total number of factors is odd. 1, 2, 4, 8, 16, leading to an odd number of toggles and leaving the locker open. For example, if locker 9 toggled by students 1, 3, 9, 3 times, which is odd, so it stays open. Locker 12 toggled by students 1 to 5 10 4 times, which is even, so it ends up closed. In summary, only perfect squares have an odd number of factors, which means they are toggled an odd number of times and remain open at the end. Moving on to the next slide, the perfect square explanation that we already discussed, and I'm going to tell again. 9 has divisors 1 3 9, 3 toggles, it will open. Non-squares like 12 has 6 divisors, even toggles, so it will be closed. Perfect squares between 1 and 100 are 1 4 9 16 25 36 49 64 81 and 100. So we'll move next slide. The final results. The final open lockers 1 4 9 16 25 36 49 64 80 and 100. The total open lockers are 100. These represent all perfect squares from 1 to 100, 1 to 10. Pattern reckoning knowledge. Divisor pairing leads to even toggles for a non-square numbers because each divisor of a number of n pairs with a distinct divisor, giving an even count of divisors. Divisor pairing, I will want to discuss divisor pairing. For any non-square number n, divisor comes in pairs d comma n by d, where d not equal to n by d. For example, 12 has divisor pairs 1 12, 2 6 and 3 4. So it has 6 divisors in total. Each divisor corresponds to one toggle of its locker. And since divisors come in pairs, the locker is toggled an even number of times. Why perfect squares are different? Perfect squares have one divisor d with pairs with itself, meaning d equal to n by d. This unpaired divisor gives perfect squares of an odd total number of divisors. Because the count of toggles equals the count of divisors, lockers corresponding to perfect square numbers are toggled an odd number of times and hence it will remain open. In essence of divisors pairing creates an even number of toggles for non-squares because each divisor has a distinct paired divisor, while perfect squares have a unique self-pairing divisor leading to an odd number of toggles. The pattern or recognition algorithms are. This problem illustrates computational simplification. Brute force simulation requires 10,000 toggle operations, which is very huge. Mathematical insight reduces it to identifying perfect squares only. Demonstrates efficiency in engineering algorithms. The engineering applications of 100 lockers is it is used to teach toggling behavior in digital logic circuits. Analogy for repeated stress testing and system state changes. It is also useful for modeling switching networks and binary state simulations. The simulations and verification. Engineering can verify the solution using simulation loops. Matrix based toggling demonstrates predictable results, reinforces understanding of discrete dynamic systems. In a sense, the conclusion are the 100 locker problem is an excellent exploration of pattern recognition. It shows how engineering thinking benefits from mathematical efficiency, and it also enhances algorithmic reasoning and structured problem solving. And we're moving. I want to conclude this with small thing. The step by step breakdown shows how the locker state changes with each tolerant. After all, students have passed only the lockers with numbers that are perfect square remains open. Lockers 1 4 9 perfect squares between 1 to 100. This happens because only perfect squares have an odd number of divisors, causing them to be toggled an odd number of times and ending as open. Each locker is toggled by 12 students, whatever the students. The problem is often it is it is a complex program which is often used to illustrate concepts in number theory particularly divisors and perfect squares. It enhances algorithmic reasoning and structured problem solving. Thank you.